The term ternary as opposed to binary implies that these next compounds will be composed of at least 3 elements instead of only 2. But the ionic part means that we're still working with those positive and negative values from metals and nonmetals, and they still have to combine in a way where the numbers will cancel each other out into a neutral compound. So ion in this case still means charged atom, but now we're going to be dealing with what we call polyatomic ions. If we break that word down, poly means many, atomic is implying the atoms, so many atoms, and then ion still means charge. So what we're dealing with here is instead of maybe one element at a time with a charge, we have these little groups of atoms that clump together and collectively have one charge overall. There is a series of polyatomic ions that you're expected to know and recognize, not just the symbol, but also their name. So the first one is going to be 1 nitrogen bonded to 3 oxygens, and the overall oxidation number of this polyatomic ion is a -1. The name of this compound is nitrate. So in this case, nitrogen and oxygen lose their individual identities, and they sort of form this new compound called nitrate, which then acts like a nonmetal in a bond because of that negative charge. The next two that you have to know and recognize are hydroxide and acetate. So hydroxide is 1 oxygen and 1 hydrogen with a -1 charge, so also acts like a nonmetal in a bond. Acetate is a little bit bigger, 2 carbons, 3 hydrogens, 2 oxygens, and again that overall -1 charge. The next two have slightly greater negative values. So we have sulfate, which is a sulfur with 4 oxygens, and carbonate, which is carbon with 3 oxygens, and both of them have a value of -2. And then our largest negative value is phosphate, which is 1 phosphorus with 4 oxygens. And then we have one polyatomic ion that's a little bit different, which is ammonium. So you'll notice probably the largest difference is going to be the value of the oxidation number. In this case, when a nitrogen and 4 hydrogens are grouped together into a polyatomic ion, they make a positive charge. So this is going to affect how they bond with other elements. They're going to bond the opposite way of all of these others that we've looked at because the charge is the opposite. So that means ammonium is going to act like a metal in an ionic bond, whereas the others would act like a nonmetal. The rules for making a chemical formula out of an ion and a polyatomic ion are the same as when we just had 2 regular ions. If an oxidation number is missing from an element, that means that you need to either know it or look it up. So sodium being in group 1 is always going to make a charge of +1. If sodium has a +1 charge and hydroxide has a charge of -1, that means 1 ion of each is all you need to cancel the other out. So the chemical formula for this is going to be sodium and 1 hydroxide. So we just bring it together just like we did before. The naming rules are pretty simple. Sodium still keeps its name the same. And rather than changing the end of the name to IDE, a polyatomic ion always keeps its original name. So this is going to be sodium hydroxide. For this substance, we need to look up the oxidation number of magnesium, which, if it's in group 2, is always going to be +2. So once again, we have a 1-to-1 ratio of charge. So that means when magnesium bonds with sulfate, it bonds in a 1-to-1 ratio. So we need to write MgSO4. Magnesium keeps its original name, and sulfate also keeps its original name. Silver is a transition metal, but it always has the same charge, so you'll see it sometimes given to you without an oxidation number on it, and that's because you are expected to remember that it is +1. So now we have a situation where the 2 oxidation numbers don't immediately cancel each other out. We would have to have 2 ions of silver in order to cancel out that -2 charge. So that means we're going to have a chemical formula of Ag2CO3. And then once again, silver being the metal keeps its name the same, and carbonate keeps its name as well. For this molecule, we're going to need to look up the oxidation number of calcium, which is group 2, so that's always +2. So we kind of have the same situation going on here where we have unequal charges, but it's a little bit different from the last one. So rather than needing another ion of the metal, we actually need another polyatomic ion of nitrate. So we're going to need to add another NO3 with a -1 charge. The way that we've been writing this then would be you would have your calcium here and you'd write your nitrate and then you would add a 2 at the very end. But this kind of presents a little bit of a problem. So it looks like there's 1 calcium and 1 nitrogen and 32 oxygens, which you know is incorrect. I mean, if you're looking at literally what's going on here, there obviously needs to be 2 nitrogens that each have 3 oxygens attached to them. So what we do here is we separate that 2 from the ion using parentheses. If we have a 2 outside the parentheses, it means we have 2 of everything within those parentheses. So calcium right here is then attached to 2 nitrates, not to 32 oxygens and 1 nitrogen. Naming rules staying the same, so whether there's parentheses or not, the naming rules don't change. Calcium is still calcium and nitrate is still nitrate. So if we look at this example, aluminum is always +3. Okay, so here's one where we kind of need that common multiple charge in order for them to balance. So we're going to have 2 overall aluminums, but then we would have to have 3 polyatomic ions of sulfate in order to balance them out. So the symbol that we're going to create in order to represent what's going on here is Al2. But then if we need to show that there's 3 sulfates, we're going to put it in parentheses. SO4 is the identity of sulfate, and there are 3 of them on this substance. Aluminum keeps its name aluminum, and then sulfate, once again, keeps its name sulfate. Okay, ammonium, a little bit different. Okay, we're going to do kind of the same style, but ammonium now is written first because if it has a positive charge, that means it's going to act like a metal. So this time we need to look up the oxidation number of the nonmetal, which is chlorine, -1. So if we have a 1-to-1 charge ratio, then that means that we just write 1 of each. So NH4Cl. And once again, the naming rules are that polyatomic ions keep their name the same. But now we're going back to this being a regular nonmetal written second. So that means instead of it keeping its name the same, we go back to those original rules where representative nonmetals will change the end of their name to IDE. If you're given the name of a substance and you're asked to come up with the formula, then that means you need to first figure out what the ions are. So potassium, group 1, it's always going to have a charge of +1. How do we know that acetate is not an element on the periodic table? Well, when we were doing binary compounds, everything ended in IDE, and this one ends in ATE. So you can kind of use that unusual name to let you remember that you need to think of one of those 7 polyatomic ions. Acetate is the one that is C2H3O2, and it makes a -1 charge overall. So if we have a +1 and a -1, that means the identity of potassium acetate is KC2H3O2. If we're trying to make the chemical formula of barium carbonate, we'll have to look up that barium is in group 2, so +2. Okay, and then once again, I can kind of use my clue that this does not end in IDE to remind myself this is a polyatomic ion. So carbonate is CO3 with a -2 charge. If the ratio is 1-to-1, then we just write 1 atom of each or 1 molecule of each, BaCO3. Alright, silver does not have a Roman numeral because it's always +1, so Ag +1. Sulfate, I know, is a polyatomic ion because of that different ending. SO4 -2. So now we have that difference in charge, which means that we're going to need to have 2 silvers to balance out 1 sulfate. So we change the symbol to Ag2SO4. Aluminum always makes a +3 charge. Nitrate is NO3 with a -1. So this is going to be a situation where we're going to need to use parentheses because that means that we need to have 3 nitrates just to balance out 1 aluminum. So if we make aluminum, we'll put parentheses with a nitrate in it and then put an additional 3 on the outside to show that there's 3 of them attached to that 1 aluminum. Zinc is one of the transition metals that always makes the same charge. And then phosphate is PO4 with a -3. So we kind of did one like this earlier where we need that overall charge to be a 6. So we're going to have 3 atoms of zinc, and we will have to have 2 molecules of phosphate in order for them to cancel each other out. Ammonium. Okay, so you can look forever on the periodic table and you won't find it. That's a good indicator that it must be one of the polyatomic ions. So we have NH4, which has a +1 charge and acts like a metal, and then fluorine, -1. So the symbol for this substance is NH4F. Okay. Now, this one I wanted to throw in there just to show you that you can have an ionic bond that's made out of 2 polyatomic ions bonding together. So if we have something like ammonium, NH4 +1, and then hydroxide, OH -1, those 2 negative charges will still react ionically just like anything else. So the symbol for ammonium hydroxide is NH4OH. And lastly, I just want to show you some examples with the transition metals because their naming rules are slightly different. So if we have a 3 and a 2, that means the chemical formula for this would be Cr2SO43. But when we name it, we need to remember that chromium, because it has multiple charges, needs to be distinguished. So if it has a +3 charge, we use that 3 to make a Roman numeral, and then we add sulfate at the end. So this one would be a 1-to-1 ratio. So the chemical formula is CuC2H3O2. But the name cannot just be copper acetate. We have to say copper 1 acetate because copper can make a charge of 2. If we have a 2-to-2 ratio, we're just going to put mercury and carbonate together. But then we need to specify in the name mercury 2 carbonate. And even though lead is not technically in D block, it is one of the exceptions to the rule. So you would be told that it had a specific oxidation number, which you need to include in the name. So we're going to need to have 4 nitrates in order to balance out that charge of +4. So we're going to put a 4 here. And then when we name the molecule, we call it lead 4 nitrate. If you're given the name and asked to go backwards, same rules as before. So the Roman numeral is letting you know what charge you need to add as an oxidation number to a symbol. So tin is Sn, and in this case it's Sn +2. Phosphate is -3. So this is going to be Sn3 parentheses PO4 2. In this case, gold would have a +1, and sulfate always has a charge of -2. So we're going to need to have 2 ions of gold for every 1 molecule of sulfate. Platinum in this molecule has a charge of +2. Hydroxide is always -1. So whenever the polyatomic ion is going to need to be doubled or tripled, we have to make sure that we use those parentheses. So we have platinum, parentheses, OH, and then we need to show that there's 2 of them. And nickel 3 carbonate. Ni with a +3. Carbonate is always CO3 with a -2. And we're going to have Ni2, and then we have to use parentheses to show that there are 3 carbonates.